All right, so now we're looking at solving equations that involve quadratics. And we've done this a little bit before, but now we're going to look at some actual, like, real life kind of situations involving quadratics, or that can be solved with quadratics. The first thing I want to do is solve here with square roots, just to kind of practice solving quadratic equations. So this is where we would add a 3 to both sides, because notice there's no middle term there. Sorry, the thing keeps zooming in on my hand. I apologize. All right, so I would get 2x squared equals 25. And then I'm going to divide both sides by 2. I'm going to come up here and do x squared equals 25 halves. And then I just want to square root both sides of that, because that's how you get rid of a squared. And so this is a weird looking answer, but this is an absolutely correct answer, that x equals positive or negative square root of 25 halves. If I wanted to, I could simplify that a little bit more, but we don't really need to do that. All right, so now I have negative 3x squared. I'm going to subtract a 14 from both sides, and that gives me 81. And then I'm going to divide both sides by negative 3. And so that gives me x squared equals negative 27. And so I'm going to take my x squared equals negative 27, move it up here so I've got a little bit more room. And I'm going to take the square root of both sides. And if you notice, what's inside of this square root is negative. So that means I can't take the square root of that. So that means that there is no real solution. So if I were to graph this, my graph would look probably something, it would be somewhere like down here, because since it's negative, it has to open downward. Since the 3 is negative, it's going to open downward, and it can't cross the axis, because if it crossed the x-axis up here, then it would have solutions. So since it doesn't have any solutions, it's down here somewhere. All right, so real life situation. A ball is kicked in the air. Its height from the ground is represented by the equation negative 16t squared plus 12t equals h, where t is the time in seconds. How many seconds does it take for the ball to fall back to the ground? So let's draw a picture of that. And I didn't mean to do that. So we have a little person, and that person is kicking a ball. Don't laugh at my stick figures. Okay, and that person kicks a ball in the air. Now, we don't really care how far forward the ball goes. We just care about it moving up. Okay, so that ball is kicked upward, and at some point that ball is going to slow down. It's going to stop moving up, and then it's going to come back down again. Okay, now that ball could have gone straight up in the air. So at the beginning, it's here on the ground, and at the end, it's here on the ground. So let's call this the ground, the x-axis. Let's call the ground 0. And so what we really want to know is, when does this ball get back to 0? Okay, so I need to find the zeros of this equation. So I'm going to set my equation, 16t squared plus 12t, and I'm going to set that equal to 0. And so I notice first that I have a t in each one of these terms, so I'm going to divide that out. Okay. And now, even though I don't have a set of parentheses here, this t is still a factor, so I'm going to break this up into t equals 0 and negative 16t plus 12 equals 0. So I already have a t equals 0, and that's at the beginning of this, like right when the ball is kicked, like just before the ball is kicked. But now I want to solve 16t plus 12 equals 0. So I'm going to subtract 12 from both sides. And if you were given a copy of these notes prior to this week, there are probably some changes to some of these equations. So just kind of cross out what you have and write in the equations that I have in here. I had to make a couple of adjustments, so stuff made a little bit more sense, or was a little bit easier. So now I'm going to go ahead and divide this by 16 on both sides. Two negatives, when you divide them, equal a positive, so 12/16. And 12 and 16 can both be divided by 4, so that's going to be 3/4 seconds. So the ball is on the ground at 0 seconds, and then it's on the ball or on the ground again at 3/4 of a second. So it probably didn't go very high, or they kicked it like super duper fast. So I just want to point out what the graph of that would look like, and I don't want you to confuse the path of the ball with the graph. So if we had this graph here, the ball starts here at 0 and it hits the ground again at 3/4. So the ball is going to go, it's going to reach its top right here in the middle somewhere. And the ball is going to get higher and higher and higher until it stops at the top. And then it's going to fall back down to the ground. Okay. So this is why the graph of that would be a parabola. Okay. All right. So here a book is dropped from a height of 20 feet. Its distance above, that should not be an apostrophe right there. I apologize. Its distance above the ground is represented by the equation -16t squared plus 20. How long does it take for the book to reach the ground? So again, this time the book is being dropped from a height of 20 feet. So that's where that 20 is. So at t equals 0, that book is up here at 20. What we want to know is as time, this is time, and this is height. As time passes, when does the book get back down to y equals 0? When does the book hit the ground? So I'm going to solve this equation. By setting it equal to 0, because I want to know when does the height equal 0. So -16t squared equals -20. I'm going to divide both sides by -16. So t squared equals, those negatives again cancel out, and I'm left with 20 over 16, which is 5/4. I divide them both by 4. So if t squared equals 5/4, I square root both sides. Now, I'm going to have a positive or negative square root of 5/4, but only one of those makes sense. Okay? Only one of these things makes sense. At -5/4, this is back here. The ball has not, or the book, has not even been dropped yet. So we don't really care about the negative. We care about the positive when the book hits the ground. Okay, and you also could simplify this because 4 is a perfect square. You could say that square root of 5/2 seconds, but either one is fine. So that book hits the ground at the square root of 5/2 seconds, which is, I think, a little bit more than a second. All right, so let's come down here. We're going to do a little bit more solving by factoring just to get some practice with this, because there are some questions on your test like this. So again, I'm going back to our x. So I want to put 12 on the top, -8 on the bottom. Okay, what are the factors of 12? Well, I have, and they'd be, okay, because this is positive, the signs have to be the same. So they either both have to be positive or they both have to be negative. Because this is negative, they're both going to be negative. And I know just by going through my factors that those factors are -2 and -6. So I'm going to do x minus 2 times x minus 6 equals 0. And then if I set each of these equal to 0, I get x equals +2 and x equals +6. Okay, now just a quick, if we had a situation where there was like something like this, and there was a number over here, remember that in order to do all this, this has to be equal to 0. So the first thing you would do would be to add a 4 to both sides, and then that's going to give you this equation right here. So sometimes you have to add or subtract something that's over here. All right, so I have another example right here. The top of my x is going to be 2, bottom's going to be 3. This number is positive, so both of my factors are going to be positive, or positive or negative. They're going to have the same sign. Because this down here is positive, that means these are both going to be positive. And my factors that multiply to give me 2 and add up to 3 are 1 and 2. So I'm just going to put those in parentheses, x plus 1, x plus 2. And then solve each one, set each one equal to 0 and solve. So this means x equals -1 and x equals -2. Okay, so here is one more word problem example, and this is kind of going back to some of the square root factoring stuff, Rocket's path can be modeled by the equation p of x equals -2x squared plus 640x, where x represents each second after launch and p is the distance in feet above the ground. How long will it take for the rocket to land? So how long will it take before the rocket gets back to the ground? So I'm going to do the same thing I did up here. I see that there's an x, but I also see I can factor out. I know that I can factor out a 32 from both of these because 64 is a multiple of 32. You don't have to do that, but I can make my life a little bit easier if I do. And I'm actually going to factor out a -32x. And that's going to give me x minus 20. And I want it to equal 0 because I want to know when it reaches the ground, which means it gets back down to 0. So I'm going to set each of these things equal to 0. So 32x equals 0 and x minus 20 equals 0. So if I divide both sides by -32, x equals 0. That makes sense because that's the beginning of our path. That's when it was launched, just like the ball being kicked up there. And then if I add a 20 to both sides, I get x equals 20. So it is going to come back to the ground after 20 seconds. So I'm going to make, let's say make each one of these little boxes, I don't know, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Perfect. So it comes back down here at 20. Now, if I wanted to sketch this graph, the vertex of my graph is going to happen halfway in between the two of these. So my vertex is going to happen here at 10. And that's going to be the highest point of the graph. So that's going to help me get a shape of my graph. So I'm going to take my original equation. I'm going to plug 10 back in there. -32 times 10 squared plus 640 times 10. And -32 times 100 is -3200 plus 6400. And that's going to give me a positive 3200. So I'm going to put that up here. Obviously, the scale on this is very different. So this would be at 10, 3200. And now I can kind of sketch my graph. And it doesn't have to be perfect. In fact, it's not perfect. It's a little too egg-shaped, but that's okay. Now, because we're talking about a thing that is happening in real life, a model rocket or a rocket being launched, we only care about this part of the graph in the first quadrant because we don't care about anything that happened to it when time was negative. Time is negative all back here. And down here, its height is negative. And we don't care about the height being negative. It reaches the ground. That's it. Like, where else is it going to go? Unless it like falls into a pit or something. So you can go ahead and I just want you to see where where these important parts are on the graph. Like, these are the parts on the graph where the rocket is on the ground. This part on the graph is the highest height that the rocket reaches, so 3,200 feet, and then how long it takes for it to get down. But you can solve these things, again, by factoring and just figuring out what your zeros are. All right. That's it.